Hi, I'm Mr. V, and today's lesson is from Illustrative Mathematics, Unit 1, the second half, which is on rigid transformations. And this is lesson 16, which is more symmetry. Yesterday or earlier we talked about reflection symmetry. This is going to be about rotational symmetry. And by the end of this lesson, you would be able to say, I can describe a rotation that takes a figure onto itself. So we know about rotations. When it takes it onto itself, that's called symmetry. And there's two kinds of symmetry. There's reflection symmetry. So if you take this and you reflect it, you end up with the same thing. And if there's rotational symmetry, and a rotational symmetry does the same thing, it ends up being on itself. So we start off with this idea of which one doesn't belong. There's four of these figures. Each one does not belong with the other for a reason. So for example, you could say A does not belong with these other three. The other three are all polygons, and A is not. It's a circle. It has no straight sides. And some people said, well, B doesn't belong because it's a triangle. Well, that's true. It's a triangle, but the other three don't have anything in common that makes B unique because it's a triangle. Same with C. C is a parallelogram. Well, it's not unique. You need to say, what does B have that the others don't have? Maybe you would say C is a parallelogram. Well, there are no other parallelograms, but the other three don't have that in common. You could say C has rotational symmetry. B doesn't, D doesn't, but A does. So saying it has rotational symmetry would not be valid. I need you to make valid comments. Each one, A, B, C, or D, does not belong with the other three because the other three have something in common that this one doesn't. So, or this one has something that the others don't have. So on C, for instance, it has arrow markings. None of the others have arrow markings. On B, it has tick marks, and none of the other figures have tick marks. So D is the only one that's shaded in. Also, you could say, let's see, B has reflection symmetry, only one line of reflection symmetry, whereas A has infinite lines of reflection symmetry. But so since it's the only one with one line of reflection symmetry, that would be a valid comment. You could say D has no rotational symmetry or no reflection symmetry, but neither does C. C is a parallelogram, a general parallelogram, and it doesn't either. So we try to see these things. On the next page, there's a video that you really should watch. This is Miss Kirkpatrick explaining rotational symmetry. And I'm not going to repeat it here just because I want you to do it on your own. There is this GeoGebra activity, though, that if you open it, you can see, and I can change the degrees of rotation. And if I look at one object at a time, for instance, if I look at the square and I go, I think it's going to be 90 degrees. And so if I go up to 90 degrees, there it lands on itself. And the next one would be 180 degrees. It lands on itself. And then 270 degrees. And so I can do that. If I look at the triangle, it's going to be 120 degrees because until I get to 120 degrees, this is a regular triangle. And you can see it's going to be like this. And finally, you can also look at the kite. The kite, the only rotational symmetry, it's an order of 1. It has to go all the way around to 360 degrees. And it's the only one with an order of 1. The rhombus, right next to it, this E2, has 180 degrees as well as 360. Same with the rectangle. So it is an order of 2. When you call it the order, every one of them has an order of 1. They can be rotated 360 degrees and land on themselves. But so you get to explore this tool and check it out. And then we consider here, draw a dot where you think the center is, and then how many squares does it take to the angle is 90, 180, 270, 360, and how many positions it would be 4. And then we can check your answer here. 1, 2, 3, 4, 4. It's got 4, or it's an order of 4 rotation, and each one of these is 90 degrees. 90, 90, 90, 90. So 90, 180, 270, 360. And then we had this one. This one I found really interesting because several people said, well, there's 5, and there's 5 points to this star. So there's going to be 5 ways that you can rotate it and land on itself and around this center. And then I asked what the angle was, and many people said it was 60 degrees. And if I were to divide this into 5 stars, or five figures going each to the vertex, you can see that I'm going to have 5 pieces. And each one of these is 360. The whole thing is 360 degrees. If I take 360 degrees divided by 5, I don't get 60 degrees. If I divide this by 5, I don't get 360. In fact, here's your solution. You'll notice it's 72 degrees each time. And there's 1, 2, 3, 4, 5 rotations. So on the next page, we talk about, I need to know the order of rotations. So is it 1? Every one of them will have at least 1, 2, 3, 4, 5, or infinite. I need to know the angle, all of the angles of the rotation. So if it's like a square was 90, 180, 270, 360. And then you can perform the rotations doing the check. And I'll do the first one for you just to show you how this works. So this is a rectangle. It's an order 2 rotation. You can rotate it 180 degrees and it will land on itself. Some people said it was 4 and tried it at 90, 180, 270. So you have to define the rotation. We're going to do a rotation. This is the center of the rotation. We're going to select the object we want to rotate. And if we chose 90 degrees, you can see that doesn't land on itself. If I do 150 degrees, that still doesn't quite make it. If I do 180 degrees, and you can see the dot, the original red dot, and you can see that this actually matches up to itself. So it's got one angle, and that's going to be 360. Oh, and then, of course, one angle of 180 and then 360. So it's got 2 is the order. Every one of them will have 360. Don't put 0. 0 is not an order of rotation. You're not rotating if you put 0. And you try this for each one of these and see what you want. And after you've tried it and do the transformation, like I just did, do it each one of them, you can come to this table on page 19, which shows all of the different ones. The regular pentagon had like 5 angles of rotation. It's an order of 5. Of course, a circle is infinitely many. And the isosceles trapezoid had 1. Wait a minute. We had a parallelogram had 2. That's right. A parallelogram had 2. Here's our parallelogram. Remember, it has no reflective symmetry. But as far as rotational symmetry, it's going to have an order of 2. I could actually transform this, rotate it to find my transformation. Here's my center. I'm going to go 180 degrees and watch the red dot when I apply it to this figure. See how it ends up at the same place. Now, my center is not exactly right, or my lines aren't parallel or something, but you can see that it's going to end up at the same place. In this activity, Claire decided this. I want you to write sentences. You can mark on the drawing. And as a spoiler alert, please do it. And you can pause this video. And then I can show you what a couple of students did earlier today. One said, if I take this point and I follow it around the circle, so I rotate it around this center point here, it'll land on this point. And it's going to be 180 degrees. How do I know that? Because when I draw the diagonal, this is going to be a diameter of this circle. In the same way, we could do, in a different color, the diameter from this circle from here to here. And if I were to rotate this point individually 180 degrees, it's going to end up on itself. And you can see these 2 points would also end up on themselves. Since it lands on itself, it has rotational symmetry of 180 degrees. Now, you don't have such thing as transformational symmetry. There's no such thing as transformational symmetry. We do have rotational and reflection symmetry. That's when it lands on itself. The closest thing we have that matches translation symmetry is what is called freeze patterns. And you can look at the pattern here. You say, well, if I take this and I repeat it down over here somewhere, I'm going to have this fence, and it's going to be the same. In fact, if I take this one little square, maybe if I take this rectangle right here and I repeat it, I translate it by this much, I can see it repeats itself here. It actually flip it, it repeats itself down here. Or maybe I take the whole thing and it repeats itself. Freeze patterns. If you're into art, this is like really cool because you can make your borders as freeze patterns, where they something that repeats a pattern that repeats itself. And this man John Conway has identified there's only 7 freeze patterns. There's only 7 of these that would exist. One is called the hop, the step, the jump, the sidle, which is like a side hop, and the dizzy hop, dizzy jump, dizzy sidle. And I'm pretty sure that that's the only ones that are. This guy's given a lot of thought to it. On page 23 is a explanation of this lesson by Miss Kirkpatrick, and then we talk about the summary. This is something that should make its way to your reference table. It tells about rotational symmetry. Here we have 60 degrees, 120, 180, and 160, 120, 180, 240 to 300 and 360. And then the final is to draw a quadrilateral that has both reflection and rotational symmetry. Sketch what it might look like and explain your reasoning. Explain why it's got rotational symmetry. Explain why it has reflection symmetry. And that's our lesson for today. Good luck and success.